So I wanted to show you this video, but I don't know if it's going to let me. There we go. Okay. So everybody take a look up on the screen. There's a little video. It's only going to be a few seconds, but what I want you to notice is what's happening to the graph when the line changes color from green to red to black. So let's take a look one more time, if it lets me. So watch it closely. What is happening as the tangent line changes from green to red to black? So when it's green, what do we notice is happening? The function is increasing. When it's red, what's happening? Decreasing. And when it's black, what's happening? You'll notice that we have hit a horizontal asymptote or a horizontal slope of our tangent. We've hit a peak or a valley, right? So what this little video is showing us is how important the tangent lines really are, because it gives us information about where our function is increasing, decreasing, or where we hit that peak or a valley. Okay, so it becomes really super helpful if we know what the tangent line is doing. And that's what's going to be discussed here in this section. So we're going to be talking about derivatives as a rate of change. We're going to talk about slopes of tangents, velocities, and rate of change. So there's a lot of physics applications that you see when it comes to derivatives. When we get to those applications, which I believe are in chapter 3, once we know the procedures of how to do a derivative, then you're going to see lots of applications for real life things. So physicists, engineers, those are a lot of applications that are most common in a calculus class. So first off, let's talk about a formula. If we connect 2 points, any 2 points on a function, if we connect those 2 points, that is a slope of a secant. So I'm going to designate that with an M with a little s next to it as a slope of a secant. So it is just the slope of a line connecting 2 points. So it's just y2 minus y1 over x2 minus x1. So a slope of a secant line is just telling us the rate of change of the function over any 2 points along the function. Now, it is customary to go from left to right, okay? So here you'll notice our secant line between P and Q changes depending upon what Q we're looking at. Now, this is the tangent line. The other ones are actual secant lines because we've just picked a random P and Q, and what's happening as we get closer and closer to P, we will get closer and closer to making a tangent line instead of a secant line. But I need you to know the difference, and this is an average rate of change between 2 points. So it's really important that you know the language, average rate of change. So it's important that you know what is referred to if they say, what is the average rate of change from time 2 to time 7, something like that, okay? But if we get closer and closer to A, then it becomes a slope of a tangent. If we get closer and closer to A, which they had called some point P is the point A, f of A. If we get closer and closer, the slope is going to represent the slope of the tangent line. So I will put a little T there to denote that. That is going to be represented by an instantaneous rate of change. If I could spell, which I can't. Instantaneous rate of change. You have to know the difference between those two things. So if the problem says find the average rate of change, or if the problem says to find the instantaneous rate of change. It is your responsibility to know that one is talking about just a slope. Calculate the slope. This one, they're only going to give you 1 point at the point A. So our x is approaching A. That's why we needed to know limits first. You'll notice that this one uses a limit. The other does not. So you have to know the difference between the language because they're going to use different terminology related to those two different things. So please make sure you know if the question in the book only uses 1 point or says the instantaneous rate of change at that point, you're finding the slope of the tangent, you need to find a limit. If it says what is the slope of the secant or the average rate of change, you just do a slope. It's nothing fancy, okay? So let's go ahead and let's actually find the equation of a tangent line using that formula. Okay, so the formula was the slope of our tangent was the limit as x approaches A of f of x minus f of A over x minus A. So that's the formula that we've got. So if they say to find the equation of the tangent line, the steps are always going to be the same. The first thing we do is we find the slope of the tangent. Second thing we do is we use the point slope formula. Okay. So we're always going to do this same kind of dance. Every time they ask us to find the equation of a tangent line, we have to know the slope of the tangent, the slope of the line. We're going to use the point. We're going to plug it into the point slope formula. So let's think about what we know. In this particular case, our A value is 1. How do we know that? Well, that's what they told us our P was, our point was. So your A is just your X value at that point. So the slope of the tangent for this particular case is going to be the limit as X approaches 1 of f of X minus f of 1 over x minus 1. So let's take out the a's and let's replace those with 1's. Now, let's just do some algebra. Does anybody notice, have you seen that before? We have. We've been doing stuff with that. That's just the difference quotient. There's 2 different versions, but that's going to really tell us that. So let's think about what is f of x. F of x is just x squared. F of 1 is 1. If I asked you to find the limit of that, you should try direct substitution. You get 0 over 0, which tells us that there is a hole in the graph. So remember, you have to fix that. So we're going to take that and we are going to factor the top and the bottom. where necessary. In this case, only our top is factorable. We're going to cross off the factors that are causing the issue. And then our simplified version should allow direct substitution. So if we plug in 1, we get 2. That's just a linear function. We are allowed to use direct substitution on any kind of polynomial like that. So the answer is 2. Now, what is that? That's our slope. So we have finished step 1. Now over here, let's do step 2. So step 2, we know our slope is 2. Our point is 1, 1. It's just the point slope formula. Now, if I know the equation, or if I know I want to find an equation of a line and I have a point and a slope, I'm going to use y minus y1 equals m times x minus x1. So let's plug everything in. So it's y minus 1 equals 2 times x minus 1. Now, you're sitting in a calculus class. I don't need you to go further. That's an equation of a line. You don't have to go any further. I know you know what to do, okay? But at least for one example, let's take the time to make that a prettier equation. Let's distribute the 2. And let's add 1 to both sides. So that is the equation of a line that should hit the parabola y equals x squared at the point 1, 1 and perfectly and only there, okay? So how can we check your work? Well, I want you to use Desmos, okay? Sorry, my window's weird. Let's see if that didn't help completely. But anyway, so if we type in the parabola, I'm sorry, it's so tiny. If we put in the 0.11, and then if we put in the equation we found, it should hit that point perfectly. And you see how it is perfectly tangent to the graph at that point. It is only hitting it perfectly at that point. I'm so sorry. I don't know why it's being weird, but so anyway, so that is how Desmos can verify that what we were thinking was correct. So let me kind of show you what the Desmos was saying. So we had r squared at the 0.11. Our line was perfectly tangent. So Desmos can verify your math for you to make sure that you found exactly what you were looking for. Do we have any questions about our first example? Okay. There's another equation or another interpretation of the slope of the tangent line, and we call h the distance between a and our second point, a plus h. And the importance of this version of the slope of our tangent is the fact that this version will always simplify. So that's the difference quotient we're most often used to. If you look in the book, they might call the first formula A or Formula 1, and the second one Formula 2. So use the book. If they say use Formula 1 to do the problem, now use Formula 2 to do the problem. Make sure that you're going back and scrolling maybe a few pages up to find out exactly what formulas they're using. It is a book. Use it accordingly, okay? Now, all this does is it just takes this distance and it gets it smaller and smaller and smaller. So our Q starts sliding over until it perfectly is a tangent slope instead of a secant slope. So the beauty of that version is, remember, it should always simplify. whether there's square roots, whether there's fractions, whether there's any funky things, it will simplify. Often it's going to give you 0 over 0. So you are going to have to do some algebra to it every time, okay? So let's look at this problem, and we are going to use the formula we saw before. So let me write that formula down so we have it. So the slope of the tangent is the limit as h approaches 0 of f of x plus h minus f of x all over h. So we've got a formula for a hyperbola, y equals 3 over x. And we want to find the equation of the tangent line at the point 3, 1. So our x value is 3. So first, let's do f of x plus h minus f of x all over h. Let's ignore the limit for a moment, and let's put in the function 3 over x into that. So it would be 3 over x plus h minus 3 over x all over h. Now, if you happen to want to verify, if you plugged 0 in, you get 0 over 0. Now, that means that there's some way that that should be manipulated. Last year we did difference quotient a little bit. This year we've done difference quotients a little bit because I wanted to prepare you that they always reduce somehow. Okay, so this is the trick you want to do with fractions. Take and put the denominators, if there's more than one term, in parentheses. Okay, we're going to multiply top and bottom by all the denominators we see. Now the bottom, we aren't going to do any multiplication. We're just going to rewrite the list, okay? But the top, we are going to actually distribute. Now here's why we did what we're doing. So if you multiply top and bottom of a fraction by the same thing, you haven't changed the fraction. You haven't done anything but manipulate the fraction a little bit. This is technically over 1. So when I multiply this here, what cancels? The x plus h's. So what's left? A 3 and an x. So let's write that down. Okay, now let's do the same thing again. Now we're multiplying this. Now remember, it's over 1. So if we multiply this by this next fraction, what cancels? The x. What's left? Yeah, so we have that negative 3, and we have still an x plus h. Do you see how now we don't have fractions within the fractions anymore? That's a trick that's always going to work. So then on top, again, the bottoms, never, ever, ever multiply them. Okay, let's not go never, but 99% of the time, just leave a little list, okay? Because what do we want to happen? We want the h to cancel out. The h in the bottom should always cancel out, right? Okay, so on top, we are left with 3x minus 3x minus 3h. What happens to these two terms? Cancel out, right? So you're left with negative 3h over h times x plus h times x. What should happen with our h's? Cancel out. So now our difference quotient simplified down to be negative 3 over x plus h times x. It should always simplify down, or you did not do the algebra correctly, okay? It should always simplify in such a way that the h that was in our denominator goes away, because that's what was causing the issue that we couldn't use direct substitution for our limit in the first place. So if you just take a moment and manipulate the algebra first, now I can do the limit as h approaches 0 very nicely. Remember, that's just going to be the slope of the tangent when we actually take the time to evaluate the limit at 0. Well, we get negative 3 over x times x or over x squared. So we get like a little formula for the slope of our tangent. Now earlier they said we were at the point 3, 1. So our x value is 3. So the slope of our tangent is just going to be negative 3 over 3 squared, or negative 1/3. So that would be negative 3 over 9, which is negative 1/3. So our first step is finally done. We know the slope of the tangent at that particular point is negative 1/3. If we were at a different point, we would get a different slope, because our negative 3 over x squared would be something different if the x is 2, if the x is 4, if the x is 7. So now we move on to step 2, which is y minus y1 equals m times x minus x1. So we have our slope of negative 1/3. Our point is 3, 1. Plug the stuff in, we got the equation of our line. So it's y minus 1 equals negative 1/3 times x minus 3. How could we check our work? Well, if Desmos works for me, and it's still being funky. I don't know why. Anyway, oh, I fixed it somehow. Okay. So how do we check our work? So we're going to put in the original equation, 3 divided by x. Okay, great. Put in your point, 3, 1. It hits there, great. Now put in the equation of the tangent line. I'm going to just type this entire junk in. Okay. So I'm going to type in y minus 1 equals my m, negative 1/3. Sorry, I suck at typing in this thing. Times the quantity of x minus 3. Oh, look what happened. Perfect tangent at that point. Perfect. Everything's wonderful and great. Yes. Oh, wonderful. So if you don't put the point in, you can verify that it is a point. Yeah, you can just touch. So the points that Desmos will show you are any points of intersection. So it's going to show you that point. It will show you x-intercepts, y-intercepts, maximums, minimums. So yeah, that's a good way to check your work as well. Okay, so there you go. That is example 2. Do we have any questions on how that worked? Okay, let's look at this one. Now it says to find the slopes of the tangent lines at 3 different points. Now, if we do it for 3 different points, we're going to just find a general kind of little a formula. We can just pop it in, okay? So remember, the slope of our tangent, we're going to use the difference quotient, is the limit as h approaches 0 of f of x plus h minus f of x all over h. Now, remember what we know. F of x is just the square root of x. F of x plus h is the square root of x plus h. Okay, so don't overthink that spot or that stuff. This is just plug in the square root into the square root x plus h. Plug in x, okay? So you guys sometimes were thinking that f is, that is just telling which function you're using. So watch that, okay? So let's plug in to our slope formula. So that's going to be the square root of x plus h minus the square root of x all over h. Now at this point, if you tried to plug in 0, you would find that you get 0 over 0, which is undefined, which tells me there's a hole, which tells me I can manipulate the algebra, okay? Now, if it's a polynomial, you're just going to kind of probably multiply it all out and factor it. If it's a fraction, we're going to use common denominators. If it's a square root, we're always going to use the conjugate, okay? So put parentheses around here. We're going to multiply top and bottom by the conjugate of that junk. Now, the conjugate of that junk is the square root of x plus h plus the square root of x. Whatever you do to one fraction, or one part of the fraction, you do to the other, okay? Now, just like before on the fraction problem, I am not going to multiply the bottoms. 99% of the time, I will never multiply the bottoms because the h needs to sit there by itself, because what's going to happen to the h? It's going to cancel if we did the algebra right. So why put it in just to have to cancel it? That's dumb. Leave it there, leave it there, leave the h there, leave it alone, leave it alone, leave it alone. Don't multiply the bottoms, okay? Because it'll just muck things up and you'll be like, what do I have there? I don't understand. Leave it alone, okay? The ones we need to multiply are the tops. You remember that good old a plus b times a minus b? Conjugates always give me the difference of squares. You better know that pattern. You're a calculus student. Don't FOIL this junk out. I mean, you can, sure. But it's just going to be the difference of squares. So what's great is it's just going to be that squared. What happens when you square a square root? It pops off the square root. And so we're just left with what's inside. What happens when we square this square root? Pops it off, just leaves what's inside. So you're left with that. So that's why you use the conjugates, because it's just first thing squared minus last thing squared. You want to square a square root so that it pops off. So does everybody see how it got to be something so nice? Hopefully. Okay, what do you notice happens on top? Where are we at? What's happening? It's just going to leave us with an h. What is going to happen then to the h that's in our bottom? They cancel. What is h divided by h? 1. Don't try to think it's 0 somehow. Anything divided by itself is always going to be 1. Okay. Can we plug in 0 now where the h is sitting? Sure, yeah. What we get is 1 over the square root of x plus the square root of x. Because the h is 0, so the h is gone. What is the square root of 7 plus the square root of 7? 2 square root of 7s. The square root of x plus the square root of x is 2 square root of x's. So that is 1 over 2 square root of x's. So that is now a wonderful little formula that tells us the slope of the tangents at any particular spot is always 1 over square root, or 2 square root of x. Okay. So remember, we had 3 points to check. Let me write our points down. 1, 1. 4, 2. And what was the other one? 9, 3. Okay. So let's find the slope of our tangent at 1, 1. Now remember, we got this beautiful formula now. Okay. So when x is 1, our slope is 1 over 2 times the square root of 1, or 1/2. When our x is 4, our slope is 1 over 2 times the square root of 4. The square root of 4 is 2, so that's 1/4. When x is 9, the slope is 1 over 2 times the square root of 9, which is 1/6. So we know that in our first one here, our point is 1, 1. Our slope is 1/2. So our equation is y minus 1 equals m times x minus 1. So that's when we are going through the point 1, 1. Our slope is 1/2. When we're going through the point 4, 2, we found a slope was 1/4. So its equation is y minus 2 equals 1/4 x minus 4. Different slope, different equation. Finally, for the point 9, 3, our slope we found was 1/6. So it's going to be y minus 3 equals 1/6 x minus 9. Okay, so there was too many for me to remember. So, okay. So our initial equation was y equals the square root of x. The first point was 1, 1. We are using the y minus 1 equals 1/2 the quantity of x minus 1. So we should hit the graph perfectly at 1, 1, which we do. We skim across it just at 1, 1. Let's put in our other one. Our equation is y minus 2 equals 1/4 the quantity of x minus 4. We should hit it at the point 4, 2. It should skim across it at that point, which it does. And then finally, our last one was y minus 3 equals 1/6 times the quantity of x minus 9. That's not what it says. X minus 9. You'll see it hits the point at 9, or the function at 9, 3. It skims across it perfectly. It is a tangent line there. So Desmos can verify your work. So use it to help you. That formula is going to be the one that most often, we don't use the first formula as often as we're going to be using this one. So please make sure that you get that into your brain. Okay. So you need that difference quotient one, because the power of the difference quotient one is it's always going to reduce. The first one reduces if it's a polynomial, because it's going to be factorable nicely, but I don't use it very often. I almost always use this one. Okay. Now, if we talk about a tangent application, oftentimes it's going to be related to velocity. So a physics application. Average velocity is just the slope of our secant. Instantaneous velocity is going to be the slope of our tangent. That is so important to know the difference. One, you use the limit. That's the tangent formula. One, you do not. So if they just say, what is the velocity at time A? They're talking instantaneous rate of change at that particular spot. That's going to be the limit formula. If they say, what is the average velocity, and give you over from time A to time B, that is the first formula, just a normal slope formula. So you have to know the difference. I cannot stress it enough. Average velocity, they're always going to give you 2 points. Instantaneous velocity, they're going to give you a point, so 1 point. That's kind of a way you can almost magically know whether they're talking about a regular average velocity slope or an instantaneous velocity slope of a tangent. Because one is at that particular point, what's happening. The other is between these 2 points, what's happening. So know the difference in that language, okay? We're going to stop here. It's not a bad idea to start looking at some of the homework that's involved. It is at the bottom of the sheet, so you can look at that. We will continue this tomorrow.